Hello! Welcome to Can We Do That? The series where we take things in the Maths A-Level and further Maths A-Level syllabus and we try and see if we can expand on them, asking the question, what happens if we alter that? What happens if we change this? What happens if we take them one step further? So with all that said, today we're going to be expanding on something we looked at in Maths A-Level, which is parametric equations, and we're going to be specifically asking the question, can we find the second order derivative for parametric equations? So with all that said, what are parametric equations? A quick reminder, instead of having a single Cartesian equation, which if you're in 2D is just linking y's to x's together, instead of that, you can have two separate equations linking the y and x to a third variable, the parametric variable. That's often either a t or a theta. And we do this for a number of reasons. Sometimes it's just so we can take the one big equation and break it down into two smaller bite-sized equations that are easier to deal with, or it's because that third variable is useful to us in the scenario we're dealing with. Like, for instance, a common scenario that parametrics are super useful for is, well, what could t stand for? Obviously, time. So you can have a separate equation showing how x is affected by time, and then another equation for how y is affected as time changes as well. So once you've got those two equations, we can then do things like calculus with them, differentiation. So for instance, we could choose to differentiate the equation for x with respect to t, and in this case you'd get 2t, and we could do the same for the equation for y, again differentiating with respect to t. And once you've got both those things, we can use them to then find dy dx, because dy dx is something we love because it's specifically the gradient of the original Cartesian curve. So if we do that, well, all you've got to do is do dy over dt divided by dx over dt, like you can see on the screen in front of you. So that's where Maths A-Level takes us up to. So therefore, as usual, I must warn you, yes, anything beyond this moment in the video is stuff you don't need to know for Maths A-Level. We're doing it anyway in this video because it's interesting to know what does happen, but we just don't need to know it for the sake of an exam. Nice. So the thing you instantly probably want to find out, or you're wanting to know if it works or not, is you're thinking, well, what happens if I just differentiate both of those equations again a second time and do the same sort of trick, divide the derivative for y, the second derivative, divide that by the second derivative for x. But you probably already saw that coming if you saw my chain rule can we do that video, but unfortunately derivatives don't work this way with second order, third order, etc., and so on and so forth. And to a certain extent there is a big clue in the notation. So for instance, why does it work with the first order derivatives? Well, it all comes down to how we divide fractions. If you're dividing a fraction, it's the same as flipping the second fraction upside down and making the divide a times. Of course, worth reminding you, derivative notations aren't actually fractions. We just write them like fractions because they share similar properties like this. Anyway, once you've done that, you notice if you were to multiply the fractions, inverted commas, together, then you would get a dt overall on the bottom, and you would get overall a dt on the top, and then those dt's would cancel, which is why you end up with just conveniently dy dx. Hooray! But if we're then looking at doing that with the second order derivatives, dividing them by each other, you can see the notations warning us that they won't cancel out in such a nice way. Now, admittedly, the issues for this is slightly different to the issues we encountered with chain rule, because actually things do cancel out. We've got a dt squared on the top of the overall big fraction and a dt squared on the bottom of the overall big fraction. They're also both denominators for fractions within fractions. But still, either way, fine enough, those would technically, I guess, cancel out. So, therefore, what's the problem? Well, the thing to be aware of is that we'd be left with a d squared x on the bottom, which is not what we want. Because if we're finding the second order derivative of y with respect to x, we want a dx squared on the bottom. It's subtle, but it is different, and therefore what we've found by dividing these two derivatives by each other is not really anything that's going to be helpful for us. So, therefore, we are instead going to have to take a step back to the first derivative stuff. However, some of you are probably looking at this stuff already and going, wait a minute, that's just two derivatives multiplied by each other, which is just the chain rule. So surely I can just do second order chain rule, basically using the stuff we were looking at in the last Can We Do That video. And so, well, I'll humor you and point out that yes, in theory, you can do that. And if you were to do that with those two derivatives, this on the screen right now is the formula you would end up getting. Brilliant. However, there is a slight problem with this, and that is if you're differentiating in the usual way that you would as part of the usual setup you get from parametric equations, you're going to be differentiating the equation with y, and you're also going to be differentiating the equation with x in. And the differentiating the equation with x in, differentiating with respect to t, means you'll get specifically a dx over dt, and then you'll also get a d squared x over dt squared, and etc, etc. The crucial part of that is you might then notice in the form below we don't have any of those sort of derivatives in there. We do have a dt over dx, and actually that isn't too much of a problem to get, because all you've got to do to get dt over dx is do 1 over dx over dt. So it's very, very easy to obtain that from the derivatives we have. But the one that causes a bit more of an issue is the d squared t over dx squared, because sadly, well, there is no super instant quick way of jumping from that to something in terms of d squared x over dt squared, etc, etc. So instead of trying to go further down that road and alter that, let's take a step back and go back to the first order definition for dy dx in terms of parametrics. And what we're going to do is a similar idea to the last video. We're going to take this and we're going to differentiate it with respect to x, because that is how you get a d squared y over dx squared, differentiating dy dx with respect to x. Okay, so in order to be able to do that, you're going to need to use quotient rule. So we're going to make the top our u, the bottom of the fraction our v, and then we're going to have to differentiate both of those things individually. So, of course, dy over dt, differentiate with respect to x, well, like in the chain rule video, a natural instinct would be to differentiate that to d squared y over dt squared. However, if we're doing that, we have differentiated with respect to t, but we weren't meant to. We were meant to differentiate with respect to x, so to correct that issue, we can then use implicit differentiation rules to correct this, because if we were differentiating with respect to t, but we were meant to differentiate with respect to x, times by dt over dx. And then similarly with the v, differentiating that with respect to x, a natural instinct would be to get a d squared x over dt squared, but again realize, oopsie, we differentiate with respect to t, we were meant to differentiate with respect to x, so do the implicit differentiation correction. Then we now have all the things we need to then start putting them in the structure provided by quotient rule. The second order derivative of y with respect to x, therefore, is going to be our du over dx times by our v. And then you might notice, by the way, if you want to, you could cancel out the dt over dx times by the dx over dt. So therefore, if you want to, you can cancel them out. Then we got to take away our u times by our dv over dx. And then the final bit of quotient rule is to divide that all by v squared. So there you go, we've found d squared y over dx squared, except you may choose to rewrite this in a few different ways. For a start, the dt over dx, as we acknowledged earlier, is not something you will have got naturally as part of differentiating parametric equations. So instead, we can replace that as 1 over dx over dt, because that's more useful. And then, because a power minus 1 technically means a fraction, and we prefer not to have fractions within fractions, something that some people might choose to do is they might choose to separate this one big fraction into two separate fractions, so that we can then move that power minus 1 onto the denominator of the second fraction. Or even some people might look at that and decide, wait a minute, I still want a common denominator, so then combine the fractions back into one big fraction with one single common denominator, and you'd get what you can see on the screen in front of you. In some ways, effectively never having cancelled out that dx from dt from the left-hand term earlier, and instead just gathering both dt over dx's onto the denominator to create that common denominator. So there you go. That is a formula for the second order derivative for y with respect to x using parametric equations. Brilliant. Okay, but it's all well and good seeing a formula. Let's have a look at putting it into use. If we have, for example, two parametric equations that look like this: y equals 5 ln t and x equals 4t to the power 4 minus t cubed. What happens if we want to find an expression for d squared y over dx squared? Well, now we've got the formula, it's easy. So all we've got to do is differentiate the y twice. So differentiate it once, you get 5t to the power minus 1. Differentiate again. It's the classic times by the power, take 1 off the power trick for differentiation at this stage. So also super easy. And then also doing the same with x. So differentiate that with respect to t once, differentiating that with respect to t again to get all these things you can see on the screen. And now that means we have all the things we need to then be able to place them in the formula we just looked at a few moments ago. So therefore, d squared y over dx squared is going to be our d squared y over dt squared times by our dx over dt minus dy over dt times by d squared x over dt squared. And then dividing that all by dx over dt all cubed. So there you go. And that is the second order derivative. Admittedly, you might choose to then do some further alterations to that, tidying it up by multiplying out the brackets in this case, because you might spot that conveniently then a bunch of things are going to gather because they're like terms. So that's all good, because then we've got the second order derivative done for us. Amazing. So there you go. That is parametric differentiation for second order derivatives. Of course, you could expand this to third order. If you wanted a formula, you would have to do more differentiating with respect to x, which might be a bit more of a chore, but you can do it. So that's, extending the idea even further. But anyway, hopefully you liked this video, so please leave a comment if you found it interesting. Like the video itself on YouTube, it always helps out this stuff. And it's worth pointing out, once again, I'm going to be doing another, can we do that some more? Please do have a look at that video if you want to have a go at some more questions of this type. And because then in that video we provide more questions and more answers, work solutions. It's all just an excuse for me to be able to do more maths as well. It's all fun stuff. Right then, and with all that said, here are some more videos you could look at. Not all the links will be appearing on the screen immediately if you're watching this video on the day it comes out, but as time goes by, there'll be links to the next Can We Do That video in the series, or maybe a previous one. There'll be the Can We Do That Some More video link for parametric second order not differential equations, just parametric second order derivatives, and then also a video for the Prove It series. Goodbye.